In the previous class on path integrals, we have defined the transition amplitude x, t, x prime, t prime is equal to k of x t, x prime, t prime is equal to integral x of t prime equal to x prime, x of t is equal to x, dx of t exponential I s. Okay, here s is the action. So the dx of t involves rigorous mathematics, and we don't have to worry about it right now. The conceptual realization of path integral doesn't require dx of t to be computed in detail. And there is another form for writing this integral, which is the Hamiltonian form. So in the Hamiltonian form, I can write the transition amplitude integral x of t prime equal to x prime, x of t is equal to x, dx of t, dp of t, e raised to I integral t prime to t dt double prime px dot minus h. Okay, now let's see some examples of simple system where path integral can be used. Free particles. The simplest case is the free particle with no interaction. If there is no interaction, then the potential will be 0. Okay, so the total action will be half m q dot square, right? Integral dt half m q dot square. In this theory, the transition amplitude is zt is equal to a time t and at 0, 0. Okay, so this I can represent as in the space time x and t. Then suppose here you have 0, 0, then here you will have 0 t. Okay, so this is t. Okay, so from this point to this point, and all there are many possible paths. So I can write the transition amplitude limit n tending to infinity m by 2 pi I delta t raised to n by 2 integral dq. Okay, so here I am taking q as the general coordinate. So I can write dq up to dqn minus 1. Then e raised to I delta t summation over I equal to 0 to n minus 1 half m q dot square, right? Now you can work out this infinite number of integral using the standard Gaussian integral formula, okay, to get the answer m by 2 pi I t whole raised to 1 by 2. So this is not a very efficient method. So there is a less mathematically rigorous method where we take the action s is equal to, okay, so half m I am writing outside, then integral 0 to t dt q dot square. So this I can write m by 2 integral 0 to t dt. Q dot square is time derivative of q, right? Now I am going to flip dt and q so that there will be a minus outside, minus m by 2 integral 0 to t dt q. Okay, then the second one as it is. Now this I can write dt, right? In the next step I am going to introduce the delta function. So minus m by 2 integral 0 to t dt. Okay, now I have to introduce delta function. So I am writing dt prime, then q of t as it is, then t minus t prime, right? So next t square as it is and q of t. Okay, so I have introduced the delta function. Now I can include this minus m also inside the bracket. Then I'll get half integral 0 to t dt dt prime q of t minus m delta of t minus t prime square q of t prime. Now here this I can write as the transition amplitude, right, q of t, then this bracket as k of t t prime q of t prime, right? So we can view the t in q as index. Okay, so a continuous index, and view this q of t and q of t prime as vectors. This implies k of t t prime situated in between the vectors is a matrix in the space of q of t. Okay, so this is very important. I can write zt as integral d q t exponential, then I, and then action. So action is 1 by 2 integral dt dt prime q k q prime. Okay, so you can see that this is similar to the Gaussian integral. Okay, so recall the standard Gaussian integral minus infinity to infinity dx e raised to minus qx square by 2 is equal to under root 2 pi by a. Okay, so this is standard Gaussian integral. Okay, then if you have more than one integral, this is very important. If you have integral dx1 up to dxn e raised to minus half xm amn xn, then this will be equal to 2 pi raised to n by 2 by root of determinant of the matrix A. Okay, Therefore, applying the standard integral zt, okay, zt is given by a constant divided by root of determinant of k, okay, because you can see that these two are same, right? These two have the same form, and therefore I can write zt as a constant divided by root of determinant k. And here you have to be very careful because this constant can be divergent, okay, this constant can be divergent, okay, but such constants will always cancel. And here determinant k is the determinant of matrix k in the space of functions, because q of t is a space of function. Therefore, k is a matrix in the space of functions. There are a lot of ways to calculate the determinant of k without using any formula. Here you have to remember that the determinant of k is the product of all eigenvalues of k. So you have to first find all the eigenvalues of k and then multiply them to get the determinant. For example, if you have a matrix A, Amn, then the vector xn, then the eigenvalue times, if this matrix acts on the eigenvector, then you'll get eigenvalue and the eigenvector, right? So the analog of this I can write as integral 0 to t dt prime k t t prime. This is our matrix. This is the eigenfunction. Then I'll get the eigenvalues multiplied by the eigenvector. So this is the eigenvalue equation. And this should satisfy the boundary condition f of 0 is equal to fi of t is equal to 0. Because what is our boundary condition? Okay, so here you can see for t equal to 0, x is 0 and it is at the same position even after a time capital T, right? It's at the same position. Therefore, I can write the boundary condition f of 0 is equal to fi of t is equal to 0. Okay. So it is an easy calculation and you can do it by yourself because the path integral is from 0 to 0. The solution is fj of t is equal to sin pi j t by capital T, and the eigen value lambda j is m j square pi square by t square. Here j will take values 1, 2, etc. Okay, and therefore the determinant k will be the product of eigenvalues. So the product of j equal to 1 to infinity, what is the eigenvalues? M j square pi square by t square. So this is the determinant. So I agree that these solutions look difficult, but this is much easier than doing the infinite Gaussian integral, right? In spite of doing all this Gaussian integral, it's easy to find the eigenvalue and then multiply them to get the determinant k, and the transition will be constant by root of determinant k. Also, most of the time finding the determinant does not require these equation, as the framework of the path integral is designed in such a way that it provides a platform to determine the eigenvalues without any explicit calculations. Okay, so let me quickly summarize the essence of what we have learned. Okay, I'll write some remarks or notes. First one, path integrals give you a new conceptual way to think about quantum mechanics. Okay, it can also be shown that the path integral approach is equivalent to the Schrodinger formulation by showing that the matrix K evaluated through the path integral satisfies the Schrodinger equation. Okay, so this is a new conceptual way of looking at quantum mechanics. Just like Schrodinger equation or the Heisenberg picture or the interaction picture, path integrals are a new conceptual way to think about quantum mechanics. Also, the wave function that is computed through the matrix K will also satisfy the Schrodinger equation. So I can write this is equal to minus 1 by 2m del x square k plus v of x k. Okay. And the second remarks is that in classical mechanics, there is a fixed path which is determined by the equation of motion. Okay, there is a fixed path determined by the equation of motion. Okay, so you have a unique solution here. So x prime, t prime, x, t. Okay, and there is a unique solution. And in quantum mechanics, you have to sum over all possible paths, right, weighted by the action, weighted by the action. So if you have xt and x prime t prime, then you have to sum over all possible paths, right? Now we are ready to learn path integral formulation in quantum field theory. So once you are familiar with path integrals in quantum mechanics, you just change the notation. You can extend it to quantum field theory and then talk about interactions. So path integral formalism for quantum field theory. Now, the dynamical variable in quantum mechanics is x of t, right? And when you go to field theory, it will be the field phi t comma x. Similarly, the overlap or the correlation xt x prime t prime becomes phi of x, right, and phi prime of x t prime. Okay, so you have to view this as a label. So this x is here a label, and we have infinite number of position. Therefore, phi of x is the eigenvalue eigenvalue of the operator phi cap t comma x. Okay, so in terms of position eigenstates in field theory, I can write this as phi of x e raised to minus I h t minus t prime phi prime of x. Here I am splitting the path to many infinitesimal segments of time intervals and then integrate it over. So the total Hamiltonian H will be the integration of volume integral of Hamiltonian density. So Hamiltonian density is pi square by 2 plus half del phi square plus v of phi. So plug this Hamiltonian in the exponential and repeat the same procedure. Okay. If you remember the correspondence between quantum mechanics and quantum field theory, then everything else will be straightforward. So if I want to calculate minus I h t minus t prime phi prime of x, then this will be equal to integral. So instead of x, here we have phi of t prime x prime is equal to phi prime of x up to phi of t comma x as phi of x. Okay, then integral d phi x t e raised to I s of phi. Okay, and here the action s of phi is equal to integral d for x Lagrangian density, which is a function of phi dot. Lagrangian density is given by minus half del mu phi minus v of phi. Okay, and what does this notation means here? D phi x comma t, right? So you have d phi xt. So this will be product over all possible values of x, right? Product over all the possible values of x d phi x of t. So last in quantum mechanics we have seen that it is dx1 dx2 etc., but here the dynamical variable is field phi, so this has to be a multiplication over all the possible values of x for the fields. And here I can write the product of t comma x, right? Product over all the values of x and t d phi x t, right? Because if you divide the time integral between t and t prime into different segments, right, then corresponding to each segment ti, I also have xi. Okay, so therefore I can write like this. So other than this additional label x, the field theory path integral for scalar field is essentially identical to that of quantum mechanics, except this additional label x. So here we can choose any potential v of phi. In case of a single particle with no interaction, the simplest form of phi, the potential in terms of phi, will be half m square phi square. Okay, so this is the potential, simple potential. So the potential is simple and also the path integral is Gaussian. Therefore, the same Gaussian integral formula, constant by root of determinant k, applies here, but in a more complicated space. K is operator in a more complicated space. So here for the transition amplitude I get constant by root of determinant k, but the thing is that in a more complicated space, k is a operator. So for interacting theory, the quantum field theory reduces to the path integral phi of t prime x prime equal to phi prime of x. And recall that our goal was to calculate the time ordering of phi of x1 up to phi of xn in this state. In quantum mechanics, you have Gn is equal to the vacuum state and time ordering of x of t1 etc. x of tn in the vacuum state. So first we will do in quantum mechanics and then we will go to field theory. Okay. So in quantum mechanics, first consider a time t1, okay, which is in between the time t prime and t. Okay, so t1 belongs to t prime comma t interval. Then I can write xt, the operator x of t1 acting on x prime t prime is equal to, okay, now I am going to insert the completeness identity. So integral dx1, right? So I have xt already here. Now I am bringing x1 t1, x1 t1, right? Then I have x of t1 as it is from here, and then I have x prime t prime. Okay, so here x1 t1 is the identity that I am inserting here. Okay, now this x1 t1 acting on x t1 will get the eigenvalue. So this will be equal to integral dx1 xt x1 t1 as it is, right? And x1 t1 acting on x, I will get x1 and then same x1 t1 x prime t prime, right? So this is the eigenvalue. Now plug in the path integral expression here. So this is nothing but the path integral expression, right? So this will be, so previously we used to all the path between xt and x prime t prime, but now we have a point x1 t1 which is in between x prime t prime and x and t, right? So here xt you have, x prime t prime you have, and in between you have x1 t1. So how does this path look like? So the path is something like, if you have t on the y-axis, then if this is x prime t prime, then if this is x t, then you have an intermediate point which is x1 t1. So first x prime t prime will go to x1 t1, then from there you have to go to xt. Okay, so now you have two different set of paths. This will be x1 t1. Okay, so first you have to do the path integral up to some location x1 t1 and then multiply it by x1, right? So from x prime t prime to x1 t1, then multiply it by x1, and then again do from x1 t1 to xt. So that is how the path will go, right? So you can see here from x prime t prime to x1 t1, then multiply by this x1 and then go from x1 t1 to xt. So this will be equal to integral x prime t prime to xt dxt x of t1, that is x1, e raised to I s x of t. Okay. So we get xt x of t1 x prime t prime as integral x prime t prime to xt dxt x of t1 e raised to I s x of t. So when we insert an operator, we translate the eigenvalue of this operator, right? Because this is equal to, see, x t x t1, right, x prime t prime. So this is equal to this integral. Okay. So if you insert an operator here in between x prime t prime and x of t, okay, then we translate the eigenvalue of this operator here. Otherwise it is just a path integral. So last class we have seen what is the path integral. This is the path integral. This is equal to integral x prime t prime xt dx of t e raised to I s x of t, right? But if you have insert an operator here, that means that we have to plug in its eigenvalue in the integrand. Okay, similarly for two operators. So now from this we can generalize for two operators. If you have two operators, x of t1 and x of t2, then we can generalize and write it as x of t1, x of t2, x prime t prime is equal to integral x prime t prime to xt dxt eigenvalue of x of t1 and eigenvalue of x of t2 e raised to I s x of t. Okay. So these two are equal only for t1 greater than t2. Okay. Because here we have seen first you have to go from x prime t prime to x1 t1, right? Then x1 t1 to, when you include one more operator, then x1 t1 to x2 t2, then from x2 t2 to xt. So that will be the path. So that's how the time ordering come to picture, right? So all these paths don't come back in time. Path always go forward in time. Therefore, in the equation, you have to insert two complete set, but the path integral cannot come back. Okay. Therefore, the order of the set of complete states have to be the same as the ordering of the path integral. Therefore, t1 must be greater than t2 for this equation to be valid. Okay. If t2 is greater than t1, suppose if t2 is greater than t1 and on the RHS you have still have the same quantity, then on the LHS we have to exchange x of t1 and x of t2 because the path integral always follows time ordering. Okay. Therefore, the correct formula which applies for all t1 and t2 so that it is always time ordered will be, right? I cannot write simply like this. I have to write a general formula which means x t time ordering of x of t1, x of t2, right? If I am writing more than one operator, then I have to write the time ordering because t2 greater than t1 will also automatically be taken care of if I write the time ordering here. right? Even if it is t1 greater than or t2 or t2 greater than t1, time or writing a time ordering operator here will take care of the issue. Okay, because always the higher time has to come first, right? T1 greater than t2 implies x of t1 should come first because time cannot go back. So this will be equal to integral x prime t prime x t dx of t x of t1. On the right hand side, the order does not matter because this is just eigenvalues and integration. So e raised to I s x of t. Okay, so time ordering ensures that x with larger time always sits in the front. Therefore, in the path integral, the time only goes forward, then the time ordering naturally arises in path integral. Okay, for any time that is t1 up to tn, which is belonging to the time interval between t prime and t, right? I can write x t time ordering of x of t1 up to x of tn x prime t prime is equal to integral x prime t prime x t dx of t x of t1, right? The eigenvalues up to x of tn e raised to is x of t. Okay. So our goal was to compute the time ordering, so that's why we choose path integral to compute it, as the time ordering is very natural in the path integrals. Okay, so now we have to see how to compute this object in vacuum state. So this is in x comma t. Now we have to see how to compute this object in vacuum state. So the vacuum correlation functions. Okay, now consider the function gn for arbitrary time, that is from t1 up to tn, which is belonging to the interval minus infinity to plus infinity. Okay, then I have to compute this for vacuum, which means vacuum state. Okay, now here instead of x of t1 up to x of tn, right, I can also write this as like this. Okay, now we have to insert the complete set of states. So here and here the completeness relation I have to use. So which relation? 1 is equal to integral dx xt and also integral dx prime x prime t prime x prime t prime. So these are the completeness relations which I have to insert here. Then I will get limit t tending to plus infinity and t prime tending to minus infinity. So from here I get t infinity and t prime will go to minus infinity. So this is the definition. Integral dx prime, right? So this vacuum state will be there, the vacuum state, and then this x of t will come here because I am inserting here, right? X of t, x comma t, then the time ordering, or I mean all the operators will be there, then x prime t prime, x prime comma t prime, x prime T prime, then the vacuum. Okay. If you observe this, you can see here this is vacuum wave function. This is also vacuum wave function. So I can write this is equal to integral dx prime. So the wave function, vacuum wave function of x and vacuum wave function of x prime. And what is remaining? This term is remaining. That is xt x prime t prime. Okay. But we already know how to do this, right? This we have already obtained. So just now we have obtained, yes, this one. So in these states, we already know how to calculate this. So I can substitute it here. So this I already know. Okay. So this trick applies to any state, not just the vacuum state. If you have any state, if here we have taken the vacuum states, if you have any state, then just insert the completeness relation, okay, and write it in terms of the vacuum. Here it is vacuum wave function. If it is any other state, then it will be the wave function in that state. Then this we already know how to compute. Okay, so for general state we can use another trick. Okay, so this integral dx prime is also not mandatory actually. Okay, so we can see some other method also where you can eliminate this dx prime. Okay, it is important in field theory because if you have an oscillator which is not harmonic and you don't know the solution of the ground state wave function, then how do you write the time ordering in, because you don't know what is the vacuum state, okay, and you also don't know the wave function in the ground state. If you don't know anything, then how do you write this time ordering? Finding gn will be difficult, okay, in such a case. So it is important in field theory because you have if you have an oscillator which is not harmonic and you don't know the solution of the ground state wave function, and also in interacting theory, if you don't know the wave function, then it is difficult to do this integral. Okay, so the new trick, okay, which is specific to vacuum state. Okay, I will start for example, limit t tending to infinity, t prime tending to minus infinity, okay, x t and x prime t prime. Okay, so I start with inserting the identity here and here. Okay, but the identity is something special here because this is equal to summation over n m. So I have x t. Now I am introducing m. Okay, that is the identity that I am going to insert here. Then I have x, then I am doing n x prime t prime. Okay, so here we have to isolate n equal to 0 and m equal to 0 states. For that I use a trick. Okay, so first I will consider this term n x prime t prime. Okay, so here limit t prime tending to minus infinity. I am just considering the last term n x prime t prime. So this I can write as limit t prime tending to minus infinity n. Then how do you get x prime t prime? E raised to, in Schrodinger picture I can write e raised to I h t prime acting on x prime. Okay, this is the Schrodinger picture in terms of the operator. And here you have to see that this n is energy eigenstate. So this is a energy eigenstate. So when e raised to I h t prime acts on the energy eigenstate, then I will get an eigenvalue multiplied by the state, right? So I'll get limit t prime tending to minus infinity e raised to I e n t prime. Okay, this is the eigenvalue, then n x prime. Okay, so here I have to apply a trick. You have to imagine that this en is of the form en multiplied by 1 minus I epsilon. Okay, of this form. Then the corresponding Hamiltonian will also be of the form 1 minus I epsilon. Okay, so by definition En is greater than the ground state energy. This energy of any other state is always greater than the ground state energy. Okay, for n greater than 0. Then here you can see this will be En then minus En I epsilon, right? So this exponential become e raised to I. Instead of En I have to write En minus En I epsilon t prime. Okay, and here limit t prime goes to minus infinity. So when t prime goes to minus infinity, you have to be very careful here. En minus En I epsilon, right? Here always En is greater than E naught and t prime is going to minus infinity, which means that this entire thing will go to e to the power minus infinity. So e to the power minus infinity means this is 0. Okay, so for any n which is greater than 0 other than the ground state, the energy eigenvalue will go to 0. Okay, therefore this integral will have two values. It will go to 0 if n not equal to 0, and for ground state n equal to 0, this will be e raised to I e naught 1 minus I epsilon t prime, then the state as it is. State will be there, vacuum state x prime. Okay, so you can see that for all n not equal to 0, it is exponentially suppressed. Exponentially suppressed. So same trick can also be used to select m equal to 0. So here what we have done, we have selected the state n equal to 0 and you have put all the other state equal to n not equal to 0 as 0, right? So using the same way, I can also select out m equal to 0 state. For that I use the other limit t tending to plus infinity x t m. Okay, this is from here, this one. So now I am taking this. Okay, so here it will be limit t tending to infinity e raised to minus I e m 1 minus I epsilon t x m. Okay, so same trick I can use here. So this will be limit t tending to infinity e raised to minus I e m, right? Then e raised to minus e m epsilon t, then x m. So if t here t tends to infinity, so if e tends to t tends to infinity, then automatically it will become e to the power minus infinity, right? Therefore I can write this integral is equal to e raised to minus I e naught 1 minus I epsilon t x 0 for m equal to 0, and this is equal to 0 for m not equal to 0. Okay, so finally what you have obtained, I have obtained limit t prime tending to minus infinity, t tending to infinity x t x prime t prime is equal to, so I have got rid of all the integrals. What I have is only psi naught. See here, I can see what all things I have left. This one, right? This is there, and these two we have already found out just right now. So this one will be, so I have to use these two also, right? This one as well as this one also I have to use. Then the remaining term will be psi naught x1 psi naught of x, right? 0. Then I have e raised to minus I. So I'm combining both, right? T prime and t. Combining both, I can write 1 minus I epsilon t minus t prime. Okay. This is if you have something in between. Similarly, I can also define the path integral limit t tending to plus infinity, t prime tending to minus infinity, xt x prime t prime as, so here I have to remove this one also. So on the right hand side I will get psi naught of x, then x, if I remove I will get 0 0 e raised to minus I e naught 1 minus I epsilon t minus t prime. So this quantity will be 1. Okay, that quantity will be 1. Therefore, I can define Gn. Okay, what was Gn? Gn was 0 x 0, right? So in any other state I can define it as limit t tends to plus infinity, t prime tending to minus infinity, x t x prime t prime divided by xt x prime t prime, right? So if I divide these two, that means this equation divided by this equation. So all the other terms are same. So psi naught star psi naught will get cancelled if I divide, right? E to the power will also get cancelled. So the only remaining term will be 0 x bar 0, right? So you get this one. The time ordering in vacuum. Okay. So even though we have calculated this often, this object is not the smartest way to calculate Gn. So this way is not the smartest way to calculate Gn. The easy way is to use the generating function. The easiest way to calculate Gn is to use generating functions. So what are generating functions? So you might have already learned in the special functions in mathematical physics. Suppose if you want to integrate something, for example, Zn is equal to integral dx e raised to I lambda f of x x raised to n. So I have an integral like this. Then we always consider a set A such that e raised to I lambda f of x plus IAX, okay, in this form. So when you expand this exponential in power series, the nth term will give you xn. Okay, the nth term of the power series expansion of this exponential will give you xn. So such a function is called the generating function. For example, ZA is equal to summation n equal to 0 to infinity ia raised to n by n factorial zn, right? Then I can obtain zn from here. So zn will be 1 by I raised to n partial derivative, nth derivative of za with respect to a raised to n at a equal to 0. Okay. So this is the general formula for a generating function. Now we have to calculate gn. Our aim is to calculate gn is equal to vacuum state time ordering of x of t1 up to x of tn, right? This is equal to integral dx of t time ordering of all the operators, then e raised to I s of x of t, right? So the generating function, to find this integral, the generating function will be something like this. Zj of t is equal to integral dx of t e raised to I s x of t plus I integral minus infinity to plus infinity dt j of t x of t. Okay. So this is the generating functional here. Generating functional, which if you expand to the nth power, you will generate this one. Okay. So instead of finding this object directly, we compute the generating functional, which makes the calculation easier. Okay, so for today we stop here and we will discuss about this more in the next class.